Can you hear me? Yeah, so my name is Hongyang, and I'll be presenting algorithmic regularization in over-parameterized matrix sensing and neural nets with quadratic activations. And this is joint work with Yuanzhi and Tengyu Ma. So there has been a line of recent work to further understand the generalization theory behind neural nets. So I'd like to start with the work of Zhang et al. So in this work, so the authors show that very large neural net models can fit real images with random labels. Since there are no useful information from the random labels, the trained model will also fail to make meaningful predictions. At the same time, it's pretty common that even when our trained model works well on the training data set, it may still fail to work well on the test data set. And finally, and ideally, we would like to find a model that fit both the training data and the test data well. So perhaps the following basic question is worth asking. So which model does the training algorithm find among the three possibilities above? So in this work, we present a case study of the above question in matrix sensing and one hidden layer quadratic neural nets that share the above three possibilities in the model. So there are a couple of challenges to answer this question. Perhaps one of the most common challenge is that the empirical risk and the population risk are not always point-wise close to each other. So let's look at the following example here. So if you look at the point here, so this point has is a local minima with a good training loss, but the test loss above turned out to be much higher than the training loss. And so I guess this example shows that there exists models that fit to the training data well, but it may not work as well on the test data. And the second common challenge is the following. So for example, if you look at the point here and another point here on the right, so the 2 points have slightly different training loss, but the point on the right has a much better test loss compared to the point on the left. So to summarize, commonly there are different local minima of similar training loss, but the algorithm has the freedom to pick the one which generalizes better. And finally, the last challenge is the practice of over-parameterization for training. So more concretely, so recent convolutional neural net architectures, they require over 1 million parameters. And so the number of parameters here could be much bigger than the number of trained images from the dataset, for example, CFAR or MNIST. So the use of over-parameterization also allows the neural net model to have enough capacity to fit real images with random labels. So let me review some of the related work in this area. So one line of work present margin bounds for neural nets. So the high-level idea is the following. If the error margin of the neural net classifier is large, then this will imply that the generalization error will be small. And more concretely, the bound may depend on the operator norm of the weight matrices of all the layers. And the second line of recent work show that the deep nets are very robust to randomly injected noise. And they connect this stability observation to derive improved generalization bounds compared to the margin bounds. So what is perhaps a little bit unclear from these two line of work is the following question. So what is the role of the optimization algorithm here? In other words, how did the training algorithm arrive at such such a model that generalizes well. So next, let me introduce the hypothesis behind the implicit regularization. And the hypothesis says that gradient descent, or its stochastic variance with proper initializations and learning rates, biases towards models with low complexity under over-parameterization. So let me unpack this hypothesis for you. So here, to measure the complexity of a model, for example, we can take the Euclidean norm of the weight matrix. And by over-parameterization, I'm assuming a setting where the number of parameters is much more than the number of training data points. So so perhaps the key point behind this hypothesis is that the algorithm plays an important role that drives good generalization performance. So there are a couple notable evidences that support this hypothesis. So this line work by Sodri et al. They show that gradient descent converges to the max margin classifier for linearly separable datasets. So a max margin classifier is the classifier that had the smallest norm among the set of all perfectly separable classifiers. And the second work by Gunasekar et al. So they studied this phenomenon on the matrix factorization problem, and they conjecture it to be true in general. So I'll be more I'll define this and explain it more concretely later. And so the contribution of this work is so we will present new evidences for the hypothesis from matrix sensing and one-hidden layer quadratic neural net problems. And we also confirm the conjecture of the previous work. So in the next part, let me describe the matrix sensing problem and our main results. But first, so let me start with a warm-up example to build some intuition first. So here, consider solving a linear regression problem on n data points, and the data point lies in a d-dimensional space. And d is much larger than n, the number of data points. So we consider running gradient descent to find separating hyperplane beta using the following least squares objective. And so it's not hard to see that there exist many solutions beta with zero objective value, as long as d is bigger than n, and there exists at least one solution. So the claim that that we like to bring up is the following. So it says that gradient descent starting with beta equal to 0 will provably converge to the following minimum L2 norm solution. In other words, among the set of all solutions that have zero loss. So why should this claim be true? So the intuition comes from the following. So if we just write the gradient of f over beta, so you can see that this turns out to be a linear combination of the n input points. And so in particular, this implies that beta only lies in the span of the n data points. And the important thing here is that we started from 0. And so if we keep adding the gradients, beta will always lie in the span of the n data points. And therefore, so the dimension of the actual search space is n, and this is much smaller than the number of parameters in beta. Okay, so let me define or review the matrix sensing problem for you. So here, so we assume that there exists an unknown PSD matrix M star, and we assume that the rank R is much less than square root D. So M star is a D by D matrix. So we have n data points A1 up to AN, and they all have size d by d, and they are all drawn IID from the random Gaussian distribution. And so we observe labels yi, which is the inner product between ai and m star for all the n data points. And the question of the matrix sensing problem is the following: given the data point ai and the labels yi, how can we recover the ground truth m star? So this is a very well-studied problem, and it can be solved via convex relaxation with O tilde d times r data points. So here, if you search in the space of PSD matrices, and you try to fit all the input data points, and you minimize the trace of x. So this convex relaxation program will recover m star. So next, we consider a non-convex formulation to solve the same problem. So here, because we're looking for a PSD matrix, so we will always write the solution in the form of U transpose. And here, we assume that the matrix variable U is a d by d matrix. So here, as I already mentioned, so here we assume that the number of data points n is on the order of d times r squared, and because we assume that r is less than square root d, so the number of data points here will be much less than d squared, the number of variables in U. So we will define the test error over a fresh sample of a random Gaussian measurement A. So in other words, we just take the expectation over the measurement A of the predicted value from the inner product of A and U transpose, and the ground truth value, which is the inner product of A and M star, and we look at the squared loss. So if you trust my calculation, so this turns out to be the distance between U transpose and M star. So we'll consider the gradient descent algorithm over the least squares objective F. So first, let's see how this algorithm works in a simple simulation. Here, so we sampled a random U star of size d by 5, and we set M star to be U star times U star transpose. And we set the number of training points n to be 25 times d. And so we will use a small initialization. Hence, the initial test error will be around 1 if normalized by the Frobenius norm of M star. So here's the result. So as you can see here, basically after this many iterations, the test error of the algorithm drops below around 0.2%. So here we do not use stochastic sampling or fresh batches. So I guess this simulation also suggests that maybe it's not necessary, as if for this problem, to use SGD. So I guess to some of the empirical evidence from this slide, so it seems that gradient descent starting with a small initialization converges to the minimum trace solution M star under over-parameterization. There is a more comprehensive experimental study also in the previous work. So next, so I would like to show another experiment that suggests that if you start from a large initialization, then it won't recover the ground truth. So here, so we consider a sample run that starts with the identity initialization. And so note that in contrast in the previous experiment that we saw, so the initialization was much smaller than the identity. And here's the result. So as you can see here, the training error drops to very small values, whereas the test loss remains on the order of 1. Yeah, so this also shows that there are multiple solutions with close to zero training loss, but large test loss in the optimization landscape. So now let me describe our main result. So in this work, we show that with roughly d times r squared, IID random Gaussian measurements, and initialization equal to alpha times identity, the test error of gradient descent at the iteration t, which is between log d over eta, the step size, and 1 over square root d times alpha times 1 over the step size, is bounded by at most alpha times square root d. So just to give you a more concrete example, if alpha is equal to 1 over d, and the learning rate is equal to this value log d squared over square root r, then the theorem shows that gradient descent will recover m star with test error at most 1 over square root d, when the number of iterations t is between square root r and square root d up to log factors. So I also just want to quickly mention that the theorem also holds for measurements that satisfy the restricted isometry property. But so a bit of technicality here is so in the theorem statement here, so we assume that m star is well conditioned. So otherwise, there will be dependencies on the condition number in all the parameters. So here, so next, so let's see how the dependence on alpha behaves in the simulation. So recall that the initialization is alpha times the identity, and here, so we will vary the value of alpha from 1 all the way down to a much smaller value, 0.001. And so we'll fix the number of iterations and the learning rates for all the simulations. And here's the result here. So the first point here is if alpha is equal to 1, then the test error will be pretty high, whereas the training error is reduced to a pretty small value. So I guess we have already sort of seen this in a couple of slides ago. And the next point here is, as you can see, so if you look at the gap between the training point and the test point, this gap starts to decrease as alpha decreases. So I guess this suggests that the generalization error does depend on alpha. Okay, so next, so let me present a simple proof sketch for the rank-1 case of the theorem. So perhaps the key intuition for the result comes from the following experiment. Here, so we plot the spectrum of the gradient descent iterates. And so as you can see here, the largest singular value of the iterates quickly grows to 1, the correct value, whereas the second largest single value of UT always remains less than 0.15, which is much smaller than the largest single value. So let me just formalize the intuition a bit more concretely. So here we define the set of approximately low-rank matrices to be the set of matrices whose second largest value here is less than epsilon. So the empirical observation we had from the last slide basically says that gradient descent only searches inside this smaller subset as epsilon. And the technical challenge that remains is the following. So how can we show that the gradient descent iterates will always remain inside this smaller subset S epsilon? And so note that the initialization already falls in this set if we start with a small initialization. And here's the proof sketch for the rank 1 case. So we assume that M star is U star times U star transpose, and U star is a vector with norm 1. And so we will decompose the iterates UT into a signal part, which is a rank 1 matrix it always lies in the correct subspace U star. And the error term, which can be arbitrary, can have arbitrary rank. So our goal would be to show inductively the following. So first, we would like to show that the error term, the operator norm of the error term always remains less than little of 1. And secondly, we would like to show that under the first condition, the signal term will keep growing at a geometric rate as long as the signal is bounded a little bit below 1. And taken together, so these two steps will imply that the UT transpose will converge to M star with error at most little of 1 in order of log D over eta iterations. So first, let's look at the dynamics of the error term. So the lemma says that actually the expectation of the error term will always shrink with t, and the norm of ET is always very close to the expectation. So here the expectation is taken with respect to the randomness of the observations A1 and AN, up to AN. So the proof goes by induction. So recall that ET is the orthogonal projection of the iterates to the subspace M star. So we write the projection here, and then because we take a gradient step, so UT plus 1 is equal to the following, and so the key step is the next one. So here the key point here is we show that basically by concentration inequalities. So for low rank matrices UT, then the gradient of f of UT will be concentrated around the expectation of the gradient. And so again, I guess I will not really bother you with the actual calculation, but if you trust me here, it turns out that the expectation of ET plus 1 is equal to ET times the multiplier here, and the multiplier is the identity minus eta times UT transpose times UT. And so therefore, so the multiplier here on the right will always contract down the spectrum of ET. And so the concentration error here is comes from the low rank matrices, and it turns out to be small compared to the expectation. So next, so let's look at the dynamics of the signal term also. So recall that we would like to show that the signal term grows at a geometric rate as long as it's bounded a little bit below the true value, which is 1. So again, so we will prove by induction here. So basically we'll use the observation that the gradient of f of UT is close to the expectation because UT is an approximately low rank matrix. And so since because the error term ET, so we've already seen from the last slide that it has a small operator norm, and so this shows that UT can be approximated by the signal term, which is U star times RT transpose. So here so we just replace the iterates with the signal term here, and we ignore the error term here. And so this calculation gives us the following multiplier. So in other words, the growth of the signal term grows by a rate of like this quantity, which is 1 plus eta times the gap between the norm of RT and 1. So this gives us the desired growth rate for RT. So just to quickly recap, so we have shown that the operator norm of ET is small, and the signal term grows by a geometric rate. And this gives us the following picture for UT. And so I mean, it's easy to show that generalization happens when gradient descent remains low rank. So we will get the following growth for the signal term. And so a bit of caveat here is So we also need to bound the Frobenius form of ET, but this can be done with similar arguments. So I guess let me just quickly ignore. So here let me show you so a very simple reduction from the matrix sensing setup to a one hidden layer neural network with a quadratic activation function. So here, so the input passes through a hidden layer with a true parameter U star, and the activation function is a quadratic function for each entry. And the output layer is simply the O1 vector. So we assume here that the inputs are Gaussian and the model is realizable. In other words, the label is generated exactly according to the ground truth model. And because of a reduction, the same technique can be used to also recover the ground truth here from matrix sensing. So just to conclude, so the key takeaway message is we showed that gradient descent starting with a small initialization converges to the minimum trace solution under over-parameterization for matrix sensing. And so the results also apply for one hidden layer quadratic neural nets as well. And for future work, it would be interesting to consider neural nets with other loss functions and activation functions. So I just want to quickly point out that there's already some concurrent work that studies logistic loss on linear conv nets. So if you're interested, definitely check it out. That's all I have. Thanks.
So we have time for questions. Yes, at the back.
Yeah, so in the simulation, it seems like actually if you start from a large initialization, then with high probability it will converge to a point that is very different from the ground truth. So I guess I showed you in one of the simulations, but yeah, so the answer is yes. No, that's just empirical. Yeah.
Yeah, Philippe.
Yeah, alpha is equal to 0 is the saddle point. So here we need alpha to be slightly big, to be necessarily positive. Yeah.
Yes, Manfred.
Yeah, so in the simplest case, your target was a U transpose, a dyad,
Yeah.
and you have a quadratic loss.
Yeah.
In some sense, a natural algorithm for this kind of problem would be the matrix exponential gradient algorithm that
I
has
see.
bounds for this kind of problem.
I see.
And you should maybe want to compare it to that
I see.
algorithm.
Yeah, I'd love to hear more maybe later.
And also,
Yeah.
how is this related to Oja's algorithm? Oja does PCA, but it does gradient descent on the U instead of the UU transpose.
Yeah, so actually, so we have a experiment for projected gradient descent also, but I sort of skipped that, but I'm happy to talk about that later. Yeah.
So while the next speaker is setting up, maybe we can have a last question. Okay, Nati.
Yeah. Uh-huh. Yeah. I see. So what kind of examples would you suggest for that? I see. Uh, well, so first of all, my intuition is the proof is robust to noise, but I'm not sure like if it's so if there's a difference between the minimum rank solution and the minimum trace solution, so that I'm not very sure. Yeah, I'm not sure if I answered your question, but I'm not very sure. But I'm happy to think more about it offline. Yeah.
Okay, so let's thank the speaker again and congratulate him on the best paper award. So now we have like three shorter talks. So the first one is about a